communicating. We use the abstract system of numbers to describe our relationship with the physical world all the time. We interact with measurements every day when we describe the distances between things, or the size of things, or the dimensions of things. And when we describe the weather and we describe different sensory experiences we have in the world, we usually abstract these things out so that we have a way of being able to relate something. It gives language to certain aspects of our physical world, in a sense. As soon as we are communicating, as soon as we had to start communicating our measurements of the physical world with other people, communicating about our measurements of the physical world with other people, it soon became clear that we had to find a standard way of knowing that we're talking about the same quantities. So a unit of measurement is something that's very important when it comes to quantifying physical relationships and physical dimensions. There should be a rigorous way for us to calculate these things. Rather than having to perform these calculations by hand, useful though they are, there should also be a way to automate these calculations. And in order for us to be able to compare two different measurements, both of those measurements have to be in the same unit, so that we're comparing apples to apples rather than apples to oranges. If we're talking about the same unit, then we know that the same quantities are describing the same aspect of a thing.
A moment. Let's try this again, shall we? So, the Systems Internationale, or the SI base unit, is an internationally agreed upon standard for the measurement of physical quantities of mass, length, time, amount of substance, electric current, thermodynamic temperature, and luminous intensity. And from these 7 base units, a further 22 units have been derived. Units for force, pressure, power, frequency, magnetic flux, capacitance, and so on. Some of the SI base units, such as the Kelvin for temperature, is only used in a scientific context, whereas others are used daily depending on where in the world you reside. The meter for distance and the kilogram for weight are a common sight in countries that have adopted the metric system. We mostly rely on degrees, either Fahrenheit or Celsius, to measure temperature, and similarly we have all of these other units of measurement for distance, mass, and pretty much the only measurement we all agree on is time, divided in 60s. We use the SI unit of distance, the meter, to describe the relationship of physical objects in space. The measure of x meters describes a distance in one dimension, whereas 2 lengths can describe the area of a plane in 2 dimensions. If we add another measure of depth, then we're describing the volume of vessels and objects in 3 dimensions. With 3 coordinates, each representing a distance from a common point, we're now able to describe the distance between physical objects in space in any direction. The meter for distance as well as the gram for weight are linear units of measurement with base 10, which means that we multiply and divide by different powers of 10 to find the larger and smaller units. So to convert between meters and kilometers as well as between meters and millimeters, we're either dividing by 1,000 or multiplying by 1,000. So these powers of 10 are always in use, and it's the same with grams and kilograms. However, when we're converting between inches and meters and feet and meters and yards and these other non-metric units, we have constants that we need to multiply and divide by. 1 inch is equal to 2.54 centimeters or 25.4 millimeters, which means that we can find a constant with which to multiply or divide the values so that we can interchangeably convert between these different units. So a value like 32 inches can be converted to 81 centimeters, 812 millimeters, or 0.812 meters. The first function we can define, for instance, is converting inches to centimeters. First, you define inches as the input that you receive from the user, and you convert that to float, of course. And then for our centimeters, this is where the actual unit conversion calculation comes in, where we multiply the inch value by 2.54 to receive a centimeter value. And we can then divide that centimeter value by 100 for a meter value, as meter is the actual SI base unit. This will then print us a formatted string which contains both the inches originally entered as well as the centimeters and meters that have been calculated. And if we were, for instance, going to use these functions somewhere in another program and we need these values to just be returned and not only printed to the terminal, we can return the output of this function as a list containing both the centimeter and the meter value. We can do something similar with feet to meters once we receive a feet input from the user. And again, return a list with centimeter and meters. We can do the same with miles to kilometers, even parsecs, nautical miles, yards, and light years. Why not? So inches to centimeters is already running and it's asking the user for its input. This is 21 inches, 53 centimeters, as well as 0.53 meters. Same with feet, 150 feet, 45.72 meters. Miles, if we walked 1,000 miles, we would have walked 1,609 kilometers. To measure vast distances in the final frontier of space, we need a final frontier in the scale of distance measurement, with a unit that's often confused to be a measure of time, but is actually a measure of distance, the light year. Now, a light year is the distance that light travels in a vacuum in a year, and this is equal to 9.46 trillion kilometers. Both 9.46 times 10 to the power of 12 kilometers for each light year, which translates to 9.46 times 10 to the power 15 meters. That's 9 with 15 zeros at the end. And converting a distance from light years into kilometers is a slightly more laborious calculation for a person, but it's very easy to even compute a massive kilometer distance very quickly. So 1 light year is equal to 9.46 trillion kilometers. So that's 9.46 times 10 to the power 12. And that's why when we enter values such as 4,500, for instance, it's an average sort of distance. It's an absolutely astronomical number. If we look at the thousands, 100,000s, millions, so billions start over here on the 7. That's tens of billions, 100s, trillions, tens of trillions, 100s of trillions, thousands of trillions, or quadrillions. So this is something like 42 quadrillion kilometers. Quite a distance. In just a few lines of code, we have 4 independent functions that can convert between different measurements of distance. And we could add any others that we can imagine, fathoms and parsecs and nautical miles and the like. We do the same for weight. If we receive value in pounds, we can see that that gives us an output of 88 kilograms. Again, our list being saved. If we need to use the outputs of these functions anywhere else, weight in ounces is equals to 283 grams. For this one, I took ounces and grams together as the output, since if you're measuring in ounces, you're not often going to get to a kilogram, for instance. You'd rather have moved over to pounds already. So the kilogram value might not be that useful, but of course it's very easy to change our function to simply include kilograms as well by dividing the gram value by 1,000. Lastly, we do the same thing for temperature. Again, temperature being the only one that's not a fully linear conversion. So where we were able to simply add or subtract constants or multiply or divide by constants for our other units of measurement, the difference between Celsius and Fahrenheit is not linear in that same way. Now, changing Celsius to Kelvin and back again is adding and subtracting a constant, which is 273.15. But once we're working with degrees Fahrenheit, to convert that into a degree Celsius, we both have to subtract constants as well as multiply by constants at the same time. So to convert from Fahrenheit to Celsius, we're first subtracting a constant of 32 and then multiplying the result by 5/9. Now, from Celsius to Kelvin, it's an easy addition of the constant 273.15 to give us the output of 313.7 Kelvin. But again, if we're changing from Celsius into a Fahrenheit, we're going to do the reverse of the previous operation. So where we had to subtract our constant and then multiply by a smaller fraction to change from Fahrenheit to Celsius, we now need to change the Celsius value by multiplying by the larger fraction and then adding the constant of 32, thereby performing the reverse of the original conversion in precisely the reverse order. So changing from Fahrenheit into Kelvin directly would require the intermediary step where we first change the Fahrenheit value into a degree Celsius value, and then we can do the linear operation of simply adding the constant 273.14. For the conversion between Fahrenheit and Celsius, degrees Fahrenheit and Celsius, a Fahrenheit value first has to have 32 subtracted from it, and the answer or the output of that operation is then multiplied by 5/9 to give us a Celsius output. So if we say it's 105 degrees Fahrenheit, we know that that's equal to 40.5 degrees Celsius. And once we have a Celsius value, we can convert that directly into kelvins by simply adding a constant again, as with all the other linear operations we did. Just adding 273.13 to the degree Celsius value tells you the value in Kelvin. Excuse me. In Kelvin. So 100 degrees Celsius is equal to 373 Kelvin on the SI scale. So that's a number of functions that can be built into an application if you need to do a lot of unit conversions, or just something neat to have on your desktop, a script that you can run from time to time. Rather than having to rewrite these functions every time that you need to use them, it might be a good idea to put all of these functions together. If we create a .py file and we copy and paste all of these functions that we've just created, then we can very quickly create a menu and interface for users to select the conversions they want to perform, input their values, and run. So this is unit_conversion.py. What I can do is import unit_conversion into any Python application that I create from here on out if I want to make use of any of these unit conversion functions. But if I want to run this directly, just add this if statement to the bottom, if name equals to main. This is for Python to check if this application is being run directly, as in the .py file, unit_conversion.py, or whether unit conversion has been imported into another .py or another Python application. If it is the case that this is the file running directly, only then will it output everything that comes after the if name equals main if statement. So in a while loop, we allow the user to select between the 8 different conversions that we can do, and depending on their selection, we run each one of these functions. So if the selection is 1, we run our inches to centimeters function. If selection is 5, we convert pounds to kilograms, and we ask the user for their input accordingly. So if we run this in the terminal, we can select miles to kilometers, and it'll ask us for our distance in miles, 150. So because I didn't enter a 9, it's going to loop and do it again. So I entered my distance of 150 miles. It output the miles to kilometers function and says 150 miles is equals to 241.35 kilometers, and then it loops back to the main menu and asks you if you'd like to do another conversion and convert 105 degrees Fahrenheit into Celsius. It gives us our output and returns us to the main menu again, and it will continue to do so until we enter 9, which will cause it to quit. And there you have it. In not a very long time and not too many lines of code, we're able to build a whole bunch of functions for unit conversion. And this is of course not an exhaustive list. If there are specific kinds of conversion that you need to do, these are functions that you can add. They'll have a similar sort of template, it's just that the details of the calculation would be different. And I've limited it to the SI units of weight and distance and temperature, but there's of course many other units of measurement when it comes to radiation and pressure, anything else that you can imagine. Just the values of the calculations would be different, and you could convert from non-standard into standard SI units by making use of these functions. And you could build this out to be a much more complete library of unit conversion functions without too much extra effort now that the initial groundwork has been laid.
I think that's enough word soup. You can jumble and chop it up in a specific way to make it seem like it was coherent, make it seem like this whole thing was planned out and poised and professional and successfully expressive. Successfully expressed. I'm going to stop talking now.